So, summing up what's happened here. So, electrons are obviously important. Electrons occur in orbitals around the nucleus, maybe a little bit abstract. Noble gases have filled valence orbitals, and so this closed shell electronic configuration tends to be more stable, which leads to them being chemically inert. So neon gas doesn't react with anything. It's so unreactive it doesn't even really interact with itself, so it's always a gas, unless you go down to very, very low temperatures, which I suspect your students will not be doing. And these noble gases tend to be like that all the way down. The other elements around them will gain not exactly the same stability. They won't be as stable, but they can be more stable if they can fill their octets in similar ways to how the noble gases do. And so all of the bonding that we talk about will be atoms trying to put electrons in those valence orbitals. Okay? So I just wanted to make another point of this. I was talking with a friend of mine that has taught a lot of these classes, and as you can probably notice, I've taken these classes but not taught many of them. And she made the point to me that she teaches at the undergraduate level, so she has freshmen coming in and taking chemistry. And she was saying that a lot of kids get taught that atoms want certain numbers of electrons to be happy. And it's kind of vague language that makes it sound like they're making friends and, they want to be happy and they want to hang out, but there's not a lot of physical motivation for what's going on. And so this language is unavoidable, I realize it. I'm using it. It's just the way that you express these ideas. But I think it's very important to also tie this language to these ideas of orbitals and how filling those orbitals leads to stability, just so there's some physical motivation for what's going on. Does that make sense? And I didn't want to talk about this too much, just because the periodic table is so big, and there's a lot that can go on in it. But like we saw at the beginning of the periodic table, when we were just talking about it, there's families that develop from this. The way we've organized it leads to certain atoms, certain elements in different rows and different columns behaving in similar ways. And so if you understand, the top of a column, that might give you information about what's going on below it. And there's all of these different properties. I just grabbed this from Wikipedia, that as you look at the periodic table, they trend in certain directions. And this kind of arises from the way we've organized it and makes it a little bit simpler to think about these things. I'm not going to talk about it so much here, but this is a very common thing, and definitely general chemistry. But even going to talks at much later stages, you'll see people who make something with oxygen, and it works well, but it doesn't quite work right. So they'll move down the periodic table to sulfur, which is similar but a little bit different, and maybe that'll do what they want. And so the periodic table gives us this ability to know which atoms are likely to be similar. Okay? So, we have atoms. They have a nucleus that has protons and neutrons in them. They have electrons around them. But a lot of them don't have filled orbitals of electrons. And so that's going to lead to them doing lots of interesting things in chemistry. And kind of the foundation of those interesting things is bonding. Okay? And so there's two major types of bonding, and definitely just two that we're going to talk about. So ionic and covalent bonds. So you guys have any idea what these are? What's the difference between ionic and covalent?
Covalent shares and ionic gives away.
Exactly, yeah. So covalent is going to be an some kind of quasi-equal sharing. And we're going to segregate this into two types of covalent bonds. So polar bonds, where it's an unequal sharing. And we're going to talk about this more. And then nonpolar, which is an uneven sharing of electrons. But nonetheless, in covalent bonds, electrons are shared between the two atoms. Ionic bonds are where they're, for the most part, not shared evenly at all. So that's the big kid on the playground going and taking something, and the little kid falling around trying to get it back. They're both close to each other. For some reason, they're attracted. Maybe it's because a toy truck was stolen, or maybe because an electron was stolen. But they're sticking close together, but they're not sharing those electrons. Okay? So, we're going to introduce another way of drawing these sorts of things. And I know this is going to make the Bohr model even more tempting, because we're going to draw electrons as dots. And so it's going to look like there's an electron sitting right there. And undeniably, it's going to look like the Bohr model. But nonetheless, this is, I think, the easiest way to kind of visualize what's going on and where a bond comes about. So recall, for example, the hydrogen atom, which is 1s1, we already figured that out. And so we can draw hydrogen as a hydrogen with one dot, so it has one electron. Okay? And so we could do the same thing for fluorine. We figured out already that it's helium with the 2s2 and then 2p5. So it has 7 electrons around it. And so we have the fluorine in the middle, and we're going to put these pairs of electrons, which represent filling in certain orbitals, and we're going to have one unpaired electron pair. And I think what makes this so great is that you can see one electron here, one hole here. It seems likely that these things might like to get next to each other and share those electrons. But just to make sure that we understand Lewis dot diagrams, because I think they're very useful for understanding these kinds of bonds, how would we go about making a lithium Lewis dot structure? Did I put a periodic table? Okay, so if we wanted to do the Lewis dot structure for lithium, how would we go about that?
Number what?
It's number 3. So for Lewis dot structures, we ignore those core electrons. So the electrons before that were hiding in these brackets, like helium or neon. Those don't go into the. Are there 3?
One then.
It would just be 1, yeah. So 2 electrons are hidden away in that core, and so lithium is here. So it's the first row. It'll just be 1 electron, 1 dot. And so since it's 1, so hydrogen is here. This is the next one down from hydrogen. It looks exactly the same as hydrogen in terms of the Lewis dot structure.
And the dot placement is important. You start on this side, or it does
matter
not
where you
matter.
put it. 1 dot. And then, so what was the other one we did? The other one we did was fluorine. So we could go 1 down from fluorine to chlorine. What do you think chlorine will look like? Maybe it would be easier if we went 1 across. We'll go through that. Exactly. So there's 7 electrons in the valence orbital, the outermost. We're going to put 7 circles around that. And so this looks exactly like fluorine did 1 above it. And so if we kept going down, if we went to, what's the next one, bromine, it would look exactly the same. Bromine in the center with 7 dots around it. Subset of the periodic table, where it's just the Lewis dot structures for these individual atoms. And so you can see it does exactly what we were showing before. Helium, 1 dot next to it. If we go down this column, they all have just 1 dot next to them. Beryllium, the next column over, has 2 dots. You go down the row, they all have 2 dots. And you can see that these correspond, in terms of these ones over here, to likely ions that would form. So you could have H+, giving up this 1 electron. Lithium+, we already worked that one out, I think. And then you could have beryllium 2+, and so on. So these are kind of show you ions that would be likely to form. You can go to the other side, to fluorine. You can see if you add in 1 more electron, then it would fill its octet. And so that is a likely ion to occur. And then chlorine is the same thing. It gets a little trickier in the middle, and we'll talk about that in the next few slides. But you can see these dot structures are very easy to come up with. Okay? So, let's talk about water. Very common molecule, hopefully most people are familiar with it. So, if we wanted to put together a water molecule, an obvious place to start is from the Lewis dot structure of the individual constituent atoms. So we have H2O, so we're going to have 1H, another H, this is H2, and then we're going to have an oxygen, right? And I've filled in all of the electrons on these things. So there's 1 electron in each one of the hydrogens, and there are 6 electrons on the oxygen. We didn't do oxygen over there, but we did sulfur, which is 1 row down. And then we can put all these things together. They can form bonds, and so we can end up with a hydrogen that has its 1 dot here, an oxygen that has its 1 dot here, another hydrogen with its 1 dot, and then an oxygen with its 1 dot. These can come together, share electrons, and this is what a bond is, sharing these electrons. And then another thing to make these things easier to draw is oftentimes pairs of dots, particularly between atoms, but sometimes even these ones over here will be replaced by lines.
Well, isn't that line showing that it's sharing that electron?
Yeah. So there would be a bond.
Yeah.
And that's a covalent bond.
In this case, it is a covalent bond. We're going to talk about how you would know. Because if we pick two arbitrary atoms, how would we know what kind of bond it is? And so we're going to talk about how to figure that out. But yes, you're right, this is a covalent bond. Okay? So, ionic bonds. We've already talked about what ionic bonds are. These are formed by oppositely charged ions attracting each other. So we have one atom that really wants electrons, and so it's going to want to be in a negatively charged state, like fluorine. And then we have another ion that would like to give up an electron in order to be in that stable electronic configuration, like for example sodium. And these things are going to come together. One of them is going to take the electron from the other one, and they're going to sit next to each other in this stable configuration. And so, for example, for the ones I was just talking about, sodium and fluorine, or a positively charged sodium and a negatively charged fluorine, they both electronically look like neon. And then the Lewis dot diagram, so of these ions, would then be sodium with nothing around it because it has no valence electrons. It's given up its one valence electron to be the plus state, and then fluorine with 8 electrons around it.
Because where does sodium start?
Sodium starts with 1. So plus would imply it's given up 1 electron. Just like what we did with magnesium where it gave up the 2 electrons. And so then you could put together the sodium fluoride molecule, and you would get a sodium plus sitting next to a fluorine minus. And we could, if we wanted to, replace these 2 dots between them with a line. It would indicate the bond between them. And just in case someday you get confused, ionic bond, it has ion in it. And so it kind of tells you what's going on in this bond. There's ions that are coming together to interact. Okay? And so a little bit more about ionic bonds. So we could think of these things. I was talking about sodium before. I didn't mean to switch, sorry. But lithium, which is similar to sodium in that it has 1 dot. We can think of lithium bringing that 1 electron to the table, so to speak, and then it can give up that 1 electron. So we have a lithium, all kinds of typos, sorry. A lithium plus here, plus an electron. And then we can think of fluorine coming in, grabbing that electron, and then you would have fluorine minus. And so you can think of this 1 electron moving from the lithium to the fluorine to form these 2 ions. I think the next slide is the same story yet again. So it's a video. So sodium,
Yeah.
but again I switched, sorry about that. So sodium comes, and here are its core electrons, so these are the ones that are not going to be involved in bonding. And then we have that 1 valence electron. It can give up that valence electron to fluorine, so we have a positively charged sodium and a negatively charged fluorine, and those things will sit next to each other in an ionic bond.
That's enjoyable.
Yes. Okay? I stole it from Wikipedia.
Well,
Exactly.
What did you say?
I cited my source, so it's okay.
Many of your teachers are called macaroni anyway.
Borrowing.
Okay. So does this
That's
idea
cool.
of an ionic bond, is it clear to you guys?
So they don't make anything together, they just sit next to each other so that they're balanced.
Yeah.
Okay.
Very cool. Sodium's watching this investment.
Which would be different than if that was fluorine?
If this was chlorine over here,
Yeah,
it would not be different. It would be the same kind of deal.
but wouldn't that make something? So
We would make
Plus
an ionic
sodium
bond,
chloride.
and so it would be another ionic bond, which would then be, so they do
she's
sit next to each
asking
other,
if
they
it's
form a
making-
salt.
Right.
And so these things are very stable, so this sodium really wants to be next to this fluorine.
Oh.
And they'll form a salt just like sodium chloride,
Oh,
table
okay.
salt.
Okay.
Yeah. But they're not going to share a bond,
Okay.
a covalent bond, they're not going to share the electrons.
Okay.
It's taken.
Yes. Okay, covalent bonds. So we've already defined covalent bonds as 2 atoms sharing pairs of electrons. So where the ionic bonds was one of the atoms one atom holding on to electrons and the other one not having electrons and sitting next to each other because of their charges. This is 2 atoms coming together with open valent orbitals and sharing electrons so that they can all fill these orbitals up. So, for example, if we have the same atom coming up, each one of them are going to be pulling on the electrons to the same degree, right? So neither one of them is going to be able to dominate this battle. So if we have H2, say, hydrogen gas, each one of them will bring one electron, so there'll be two of these. They'll come to the table, they'll put their electrons near each other, and they'll be able to fill that one s orbital between the two of them. And H2 is a relatively stable gas.
And it would overlap. Okay.
Yes. So molecular orbitals forming from atomic orbitals, overlap is very important.
Okay.
And covalent is not quite as snappy as ion being in it, but covalent is covalence. So these valence.
Cohabitating.
Yes, exactly. Okay? So restating the same thing again, covalent bonds occur when two atoms share electrons to fill those outermost orbitals. Some atoms will share evenly, so like O2, it's just like H2, it's the same atom coming in, and so they're going to each be pulling to the same degree, and so they're going to share those electrons evenly. Others will not share evenly though, and we're going to talk a little bit more about this, but you can imagine oxygen. It was to the right on the periodic table, and we know the ones on the right really want electrons. And then hydrogen is all the way on the left, and so it kind of wants to give up electrons. And we're going to talk a little bit about understanding how much they want to give up electrons and how much they want electrons on the next few slides.
Is it possible to get like a group of, oxygen that's not going to, like a positively charged altogether? You know what I mean? Like you're saying, it's a positive one is bonding with the negative one. Is it possible just to get a bunch of positive ones in a lab or you know what I mean?
So you're saying, is it possible to make like oxygen, which wants to be negative, positive? Is that the question?
Just having them not bond together. You know what I mean? Is it always bonded together?
Oh, so like oxygen, will you just get one oxygen?
Yeah.
No, that would be very unstable.
Right.
So it's either going to steal electrons or it's going to bond with something.
Okay.
But you could get an oxygen that has a positive charge on it if you just got something next to it that wants electrons even more than it. Or I'm sure through some nuclear process you could spit out a positive oxygen, but it wouldn't be stable.
Right.
So, restating the last slide. So there's these two kinds of covalent bonds. We can think about them as a tug of war occurring between the two nuclei. So in the case of O2, I really wanted a picture of myself playing tug of war, but I didn't have time to Photoshop that together. But I was able to find this guy playing tug of war with himself. And so the two oxygens are pulling, and they have the same number of protons in the nucleus, so they have the equal ability to pull on these electrons. So the electrons will be shared evenly between the two oxygens. But with oxygen and hydrogen, or between any two elements, there'll be some discrepancy in their ability to pull. And sometimes that discrepancy will be very small. Like if you think about moving down the periodic table from oxygen to sulfur, those are very similar, they have similar octets. So the difference will be similar valence electrons. So the difference will be very small there. But in the case of oxygen and hydrogen, that difference is pretty large. And so it's, like playing tug of war with someone much stronger than you, you'll lose that battle and the electrons will be shifted over. Okay? And so this is, I think now we've kind of defined it in this arbitrary way, but we can quantify it to some extent. So some bonds are ions electrostatically attracting each other, so that plus charged ion and the minus negatively charged ion sitting next to each other. Some of them are sharing electrons to some degree, but we wanted to be able to know the difference between these things, how to distinguish bonds like that. And so the way that we typically do this is with something called electronegativity. So electronegativity is the tendency of an atom to attract electrons to it. So how much does a particular atom want electrons? And so the larger the value of electronegativity, the more an atom wants electrons. And so electronegativity depends on pretty much two important things. The atomic number, so how many protons are in the center. And in terms of this, remember those core electrons are Yeah, I'll leave that aside. So the atomic number is what's important, how many protons are in the center, and then the distance of the valence orbitals from the nucleus. So the bigger the atom gets, the less tightly those outer electrons will be held on. And so if we go to a periodic table where I've indicated the electronegativities, you can see the fluorine over here has the largest electronegativity on this table. It wants electrons the most. It's the smallest one that by gaining one electron it can be like a noble gas. So it's the smallest atom here, and it needs to gain the least number of electrons to become like a noble gas. Down here, chlorine needs to gain the same number of electrons, but it's a little bit bigger. So those electrons are a little bit farther out there, so the electrostatic interaction between the nucleus and those electrons that are a little bit farther away is going to be a little bit weaker. And so you can follow these trends. So as the atoms get bigger going down, the electronegativity drops a little bit. And then likewise, as you go to the left, as the number of protons in the core gets a little smaller, the electronegativity also drops. And so over here, atoms really want electrons. Over here, they don't want them so much, and they're willing to actually give up their electrons. And so electronegativity quantifies how much they want electrons. And so we can use these things to understand how, given two atoms sitting next to each other, how are they likely to share electrons? Okay?
We
So
go back one slide for just a quick second.
Sure. Electronegativities, we can use them to try and understand molecules. First thing, this slide just wanted to point out some more trends in this. So the fluorine here is this atom right here. And then we can look at what happens to the electronegativity as you change the number of protons in the core. So I guess I should have started over here. Lithium. So lithium is right here. As you add in protons, it wants electrons more and more and more. And then it reaches that point where it's like neon, and then it drops off again to be like sodium over here, where it doesn't really want electrons. And then it grows and grows and grows. And then it does something similar when you go to potassium. And then it'll grow, and then it goes through this weird region where we reach the transition metals, and then it'll come back over, pick up over here, where we get back into the P block and start growing again.
So does that mean that the elements that are closer to those noble gases are more unstable? Is that a way?
I wouldn't say they're more unstable. I would say they want electrons. These ones over here still are unstable in the same way. They still want to react and form bonds, but they're going to engage in bonding differently.
Okay.
So these ones are going to want to give up electrons. These ones are going to want to gain electrons.
But then they're gonna. So is the tendency for the ones on the center to pair up with ones on the
Yeah. On the ends, they tend to pair with each other to form ionic bonds.
Okay.
We'll talk about that.
Yeah.
Okay. So distinguishing ionic and covalent bonds, we have this metric to understand how much an atom wants electrons, the electronegativity. So diatomic molecules of the same atom, they both have the same electronegativity. We talked about this before. It's like playing tug of war with yourself. They're both going to pull on those electrons to the same degree, and so those electrons will be shared equally. The difference in electronegativity will be zero. So if we take the electronegativity of one atom, subtract the electronegativity of the other one, it's going to be zero for a diatomic molecule of the same atom. And so those electrons will be shared equally. So if we look at how ionic particular bonds are, plotted versus the electronegativity difference between the two atoms engaged in the bond, we can see that it's zero for chlorine, and then it climbs way up for the two atoms that we saw before on the opposite ends of that chart. So lithium and fluorine. And so it becomes very ionic-like when they're very different in electronegativity, and it's entirely covalent when they're exactly the same, when it's chlorine. Okay? And so we're gonna, I think, move on to to how we actually use these to quantify. So greater differences in electronegativity means greater ionic character. So one of them is winning that tug of war battle. And so what we can do is we can take the difference in electronegativity and partition it into these different types of bonds. So if they're very similar, the difference in electronegativity will be small, and those are non-polar covalent bonds. So typically between like 0.5 and 0 would be a non-polar covalent bond. You want to retain for these things. And what I want to talk about in terms of molecular properties right now, and we can talk about a bunch of these properties in terms of our fundamental understanding of molecules. But the one thing I want to talk about is the melting process. So going from a solid to a liquid. Okay? So the process where a solid goes to a liquid would be like when you freeze ice in a freezer. Obviously it starts out as a liquid, it goes to a solid, you can take it out, it'll go from a solid back to a liquid. So there's this phase transition that's going on. What was that?
And you can even have it evaporate.
Exactly. We could look at other transitions that go on. Yeah. And you could rationalize those transitions in the same way. I'm just going to talk about one of them here, but you could talk about them all in the same way. And so the point I wanted to make is our understanding of these different types of bonding, so how polar these different bonds are. So ionic molecules occur when you have a positive charge next to a negative charge. This is a very highly charged situation, right? These things are holding onto each other very tightly because of these charges. And then you have a slightly less polar situation where you have polar covalent bonds, where they're sharing electrons, but there's still a charge difference formed by the way that they unequally share these electrons. And then we have the noble gases, and we have non-polar covalent bonds where there's no charge formed. So the electrons are held in between them, but they're shared equally, and there's no charge distribution formed across this bond. So we have these three different cases. And what these three different cases means is that in these polar situations, we have essentially little magnets. And these little magnets, these little molecules that look like magnets, can line up with other molecules that look like magnets. And they'll attract each other, and it'll be very favorable for them to sit next to each other. And this will mean that it's much more stable for them to be next to each other and to be ordered. And so going down this chart, we have three examples of it. So we have O2, where electrons are shared evenly, a covalent bond. We have water, where we have electrons shared unevenly, and it's a polar covalent bond. And we have lithium fluoride, which is an ionic bond, which is very polar. And you can see the masses are relatively the same here, so the sizes of things aren't changing that much. But the melting point changes dramatically. It goes from being a very small value, so oxygen is a gas for pretty much all of the temperatures we will ever encounter, right? So these things aren't interacting very strongly. It wants to be a gas. Water interacts relatively strongly with itself. So it has a polar bond, and that means that it ends up being a solid at relatively moderate temperatures that we encounter all the time during the winter at least. And then lithium fluoride, where we have these charged particles sitting next to each other, they interact very strongly, and it actually doesn't melt until you get to a very, very high temperature. And it's likely a temperature you would never encounter. And so salts like this will tend to stay solid up to very high temperatures. Polar molecules tend to be liquids at room temperature. Some of them tend to be liquids at room temperature. And we tend to be able to observe some of these phase transitions in our kind of everyday lives. I guess water is really the main one, but like dry ice is another one that's relatively close to our temperatures that we encounter, and so you can buy it at the store and so on.